In this video, I will show you how you can solve a constraint optimization problem with inequality constraints using the Lagrangian method. So let's start with the maximization problem. In particular, we want to maximize with respect to x1 and x2 the objective function square root of x1 times x2 under the constraints such that x1 squared plus x2 squared is less than or equal to 5 and x1 and x2 are greater or equal to 0. So we have these three inequality constraints and our objective function. Now before we actually optimize, we need to check the constraint qualification, for which we need to put the constraints into the correct form. The correct form of a constraint is g of x is less than or equal to 0, where g of x is the constraint. Now, if you look at this constraint here, it's very simple to put it in this order, because you can just subtract 5, and then everything is on the left and a 0 to the right. These two constraints here are more complicated, because you say x1 is greater or equal to 0. However, we can multiply them by -1, and then they're in the correct order. So let me rewrite all three constraints in the correct form. So we have x1 squared plus x2 squared minus 5 is less than or equal to 0, minus x1 is less than or equal to 0, and minus x2 is less than or equal to 0. This allows us now to check the constraint qualification. In particular, the constraint qualification is the vector of first order conditions with respect to our endogenous variables of the objective function. Okay, so let's start with the first one here. So we get 2x1 and 2x2. The second one we get -1 and 0, and the third one we get 0 and -1. And we get our matrix actually of first order conditions. Okay, now we need to check that this vector has full rank for all binding constraints of this Lagrangian. Well, first off, we know that never all three constraints can bind simultaneously, because if x1 is equal to x2 is equal to 0, this expression will be less than 5. The first order condition of the first constraint has rank 0, provided x1 is equal to x2 is equal to 0. But by these two constraints down here, we know that we will have these other vectors, and this one is indeed not binding if that's the case, so we can omit that point. Now, if x1 is 0, we have this middle vector that we need to look at. And if the top one is binding, then we will have 0 and 2x2. And x2 is greater than 0. So these two vectors will span R2, and the constraint qualification is satisfied too. Similarly, if x2 is equal to 0 and the first constraint is binding, then we have these two where we have a 2x1 here, where x1 is not equal to 0, and 0 here. So this vector and this vector will span R2, and the constraint qualification is satisfied. If the constraint qualification was not satisfied, we will need to check any point for which it's not satisfied if that point is also a maximum or a minimum of our constraint optimization problem. So in particular, if I drop these two constraints, I would need to check the point 0, 0 at the end. Let's set up the Lagrangian and solve this constraint optimization problem. L equals square root of x1 times x2 minus the first Lagrange multiplier, lambda 1, times x1 squared plus x2 squared minus 5. Now, minus the second Lagrange multiplier, but remember that here minus lambda 2 times minus x1, because we have to flip it to get the constraint in the right form. So we can do plus lambda 2 x1 plus lambda 3 x2. And we set up our Lagrangian. Now we need to find the first order conditions. So let's start with Lx1, which is simply 1 over 2 x1 to the minus 1/2 x2 to the 1/2 minus lambda 1 times 2 x1 plus lambda 2 equals 0. Now the Lagrangian, the first order condition with respect to x2 is equal to 1 over 2 x1 to the 1/2 x2 to the minus 1/2 minus 2 lambda 1 x2 plus lambda 3 equals 0. So we have our two first order conditions. Given these are all inequality constraints, we don't take the derivative with respect to the other Lagrange multipliers, but we put the complementary slackness conditions down. The first one is lambda 1 times x1 squared plus x2 squared minus 5 equals 0, and lambda 2 x1 equals lambda 3 x2 equals 0. To conserve vertical space, I put them into the same, and we have our three complementary slackness conditions, and the last condition that lambda I is greater than or equal to 0 for all I. And we have all our conditions, so the two derivatives, because we have two variables in the objective function, the three complementary slackness conditions, 1, 2, and 3, and the condition that each Lagrange multiplier is greater or equal to 0. Okay, now we need to solve that. Well, given that we have three constraints, any of these three constraints could be binding or not. So we would have a lot of combinations to solve. We know that the square root of x1 times x2 is equal to 0 if x1 or x2 equals 0. Right? So if either of x1 or x2 is equal to 0, this objective function is 0. Now let's assume one of the two is slightly larger than 0, then putting in a positive x2 will make this function value go up. This means that x1 equals 0, x2 equals 0 can never be a solution. So x1 is not equal to 0 and x2 is not equal to 0. Okay, that simplifies a lot. We just got rid of this constraint here because it holds with strict inequality, right? It's not binding. If it's not binding, we can get rid of these Lagrange multipliers and we can simplify our problem accordingly. Voila. Much easier. Now, if we look even closer, we can also argue that lambda 1 cannot be equal to 0. Let's look back at this objective function. So the square root of x1, x2 is strictly increasing in both x1 and x2. So that means if I take a slightly higher value of x1 or x2, the function value goes up. But that immediately implies that this constraint is binding. The reason for it being, assume this constraint is not binding. So x1 squared plus x2 squared is less than 5. Now if it's less than 5, I can increase x1 or x2 just a little bit until this thing is binding and I have a higher function value. So this implies that this expression here, erase that, is equal to 0. Okay, so we have lambda 1 equals, is not equal to 0 from this one. So we went actually down to one case. There's only one case which we cannot exclude. Okay. So if there's only one case, we can rewrite this a little bit more nicely. This equals 0, this equals 0. Well, we have these two constraints and this third expression which has to be equal to 0, and from which we can get x1, x2, and lambda 1. Note we need to solve for lambda 1 as well. Okay, how do we get it? Well, we solve these equations. So the first one, let's solve for 4 lambda. So we multiply by 2, divide by x1, and take 4 lambda to the other side, and we get 4 lambda 1 is equal to, so we divide by x1, so x1 to the minus 3 halves times x2 to the 1 half. Okay? From the second one, we get almost the same. 4 lambda 1 is equal to x1 to the 1 half and x2 to the minus 3 halves. Putting the two equal to each other, we can get the following. So we get, you write that below, x1 to the 1 half times x2 to the minus 3 halves equals x1 to the minus 3 halves times x2 to the 1 half. Wow. So we have this. Now let's multiply both sides by x1 to the 3 halves and x2 to the 3 halves, which will lead us simply to have 4 halves here, so to the power of 2, and 4 halves here, and we're left with x1 squared equals x2 squared. So, wait, now we can have several solutions, right? x1 and x2 could be negative. Well, but wait, our constraint here says otherwise. Given this constraint, they both have to be positive. For that, there's only one solution, where x1 squared is equal to x2 squared, which implies that x1 equals x2. Okay? Now that we've set those two equal, we can plug them into this constraint here, this binding constraint, and we will find that both x1 and x2, right? So in this constraint, if we square this term, we know that two are equal, so we get 2x squared, xi squared is equal to 5, right? So we can divide by 2 and take the square root, and we got x1 equals x2 equals 5 over 2. Okay, are we done? No. We need to find lambda 1. We know that lambda 2 and 3 are equal to 0, as we defined before. But we need to find lambda 1. Lambda 1, well, we know that, I already erased it, so let me make some space and get rid of the first order conditions for now. I will put them back up shortly, but let's get rid of that for now. And as well as the Lagrangian here. And if you remember the two first order conditions that we solved for lambda, we had for lambda 1 is equal to x1 to the 1 half, x2 to the minus 3 halves, right? Well, since x1 is equal to x2, I can replace this with x1 here. I get exactly the same result, but then I can multiply these two, which lets me with x1 to the minus 1. Okay, nothing is easier than that. That's just square root of 2 over 5. Now I need to divide it by 4 times 1 over 4, because here's 4 lambda 1, and I got my lambda 1, which I can rewrite as 1 over 40, or the square root of 1 over 40. So I got my solution. Lambda 2 and 3 equal to 0. Lambda 1 equals to square root of 1 over 40. And we verify that's a positive number, so we're fine. And x1 and x2 are equal to each other. They're equal to 5 over 2 square root. To the square root of 5 over 2. Okay. Well, we're not done. We need to find the second order condition to check if that is indeed a maximum or if it is a minimum. Note that the minimum will be easily found because it's a corner solution, so the objective function will be 0, so it's very likely that this is a maximum. But we still need to check. Okay, so let's rewrite the 3 first order condition under the binding constraint. So if we optimize with the binding constraint, we take the derivative with respect to the Lagrange multiplier as well. And let's start with that. So we get the derivative of the Lagrangian with respect to the Lagrange multiplier is equal to x1 squared plus x2 squared minus 5 equals 0. Note that's actually wrong because there are some minus signs here. Okay? Because in Lagrange we had minus lambda times this, and times this. Then we have the derivative with respect to x, 1 over 2 times x1, x to the minus 1 half, x2 to the 1 half, minus 2 lambda 1 x1 equals 0, and Lx2, which was equal to 1 over 2 x1 to the 1 half, x2 to the minus 1 half, minus 2 lambda 1 x2 equals 0. So we have our 3 first order conditions, so we can set up the ordered Hessian. So if we take the derivative of this with respect to lambda, we get obviously 0. If we take the derivative of this with respect to x1, we get minus 2x1. Then we get minus 2x2 for the last one. Okay. Now let's start with this middle term, which is the most complicated one. So what we get in here is 1 over 4 with a minus sign, since it's minus 1 half, times x1 to the minus 3 halves, x2 to the 1 half. Okay? And we have this term here. With respect to x1, we get minus 2 lambda 1. Then above it just repeats, so we get minus 2x1. And at the bottom, we take the derivative of this with respect to x2. And we get 1 over 4 x1, x2 to the minus 1 half. Okay? Then, to the far right, let's start with this term because it will be the biggest. It's symmetric, so it's almost the same as here. So what we get is minus 1 over 4 x1 to the 1 half, x2 to the minus 3 halves, minus 2 lambda 1. Above that we get the same as here because it's a symmetric matrix, 1 over 4 x1, x2 minus 1 half, and on top minus 2 x2. And we got our ordered Hessian. Okay, now given there's very little space to the right, let me erase the top part, first order conditions. And figure out the determinant of this ordered Hessian. So the determinant of the bordered Hessian is equal to, okay, so we have the diagonal term in the middle, which is 0. Then we have this term times this term times this term, and this term times this term times this term. But they're both the same. Join them together, we get 2x1, x2 to the 1 over 2. Note that x1 times x2 times the square root the negative of the square root of the 2 just gives us the square root of the 2. Right? Okay, we have this term. Next term is the negative terms. So let's start with the diagonal. So we have the same here. And we have 3 minus sign, so it becomes plus. The 2's cancel again. So that's gone. Then we have x2 squared times x2 square root. So we can rewrite that as 5 halves x2. So we're left with x1 to the minus 3 halves, x2 to the 5 halves, right? X times x is 2. 2 plus 1 half is 5 halves. We mustn't forget this term, which is simply plus a lambda 1, x2 squared. Don't forget the x's, right? So you have this term, and then we have the other one, so this is the main diagonal, then we have this diagonal here, this and these two terms, which is simply the same, just with x1 and x2 replaced. So we get x1 to the 5 halves, x2 to the minus 3 halves, plus a lambda 1 x1 squared. Okay, we have this expression. Now, we already ruled out that the x's are equal to 0, and we said that the x's are positive. So this is a positive term, this is a positive term, and this is a positive term, and these two terms are positive provided lambda is greater than 0. Well, that means the whole thing is greater than 0, because we just found a lambda to be square root of 1 over 40. Okay, so we found the determinant of this bordered Hessian is positive. Well, since it's a bordered Hessian with one constraint and two endogenous variables in the objective function, we know that we just need to check the overall determinant of this thing, and if the overall determinant is positive, we have a maximum. Okay, so going back, we first set up the Lagrangian, we check the constraint qualification. If the constraint qualification does not hold, for a certain point, we need to include these points at the end to check if they're actually a maximum or minimum, depending on the problem we have. Then we set up the Lagrangian, we set up first order conditions, solve for the x's and lambdas by first checking if we can exclude any cases to make our life simpler. If we cannot exclude any case, we need to go through all combinations plus the points we got from the constraint qualification. In this case, that would be 8 points, because there are 8 combinations of the lambdas being positive or negative. Being positive or 0. Now, I ruled 7 of those out, so I'm left with 1 possibility, and I saw that the constraint qualification in this example holds for all points. So we got this one solution, which we need to check the bordered Hessian for. Now we check the bordered Hessian for the entire Lagrangian, and it turns out that this bordered Hessian is positive definite, which means in turn that the whole Lagrangian is concave, or quasi-concave at least. Given that the objective function is at least quasi-concave throughout all points, we can be assured that it's a maximum. But we can also plug in all the function values and find everything's positive, all terms are positive. So at the point, this bordered Hessian is strictly greater than 0, which means we found a maximum. Thank you for watching.